Hello, I'm Dr. Ian McCullough from Johns Hopkins University, and in this lecture, we are going to use a machine learning algorithm, in this case a decision tree, to aid in decision making surrounding loan approvals for a financial institution. This is only illustrative to show you how the AI lifecycle might work in practice. So we're going to begin using our ROAD methodology with the requirement. It's very important in any type of AI project that we have a clear understanding of those requirements. And even with these clear definitions right now, there's a lot that goes into the whole process of loan approval that is still left unresolved. Like, how do loan officers make decisions today? Are there any concerns or issues that banks have with the way those decisions are being made? For example, Visa is looking at financial equity around the world. So a lot of decision making around loan approval is based on a Western model. So if you are in the developing world, you might do all this business from your phone, and you might be trying to start a business, and you'd be a great bet for a loan, for a business loan, but you don't have a bank account. Well, by Western standards, you're probably not going to get approved for a loan. So do we need to do something different in different geographies or in different populations to better understand how we can actually have financial equity around the world? Are there other pain points? Like, is a financial institution having a greater amount of defaults? Does the economy or exogenous factors affect that? There's a lot that goes into this that we're not even going to begin to scratch the surface on. And it's for these reasons that it's very important to have domain experts involved in the requirements definitions. And, if you're the data scientist or the AI practitioner, you need to enter into conversations with the domain experts to try and tease out what some of that tacit knowledge is, understand the processes that they're trying to work through, and maybe collaboratively identify pain points or opportunities for improvement, or even what the data is. Well, the next step is how we're going to operationalize the data. So in the data set that I'm going to be looking at, we have several fields that we are actually able to pull from the database. So the ID is a unique identifier for a borrower. We can understand if there's a delinquency status. So this is telling us whether a given borrower in the data is delinquent on a loan, meaning they haven't been making their payments or not. We can look at the duration of the loan, the gender of the borrower. Now, sometimes people want to be race unaware or gender unaware because they think that there's an ethical issue with that. In this case, we do have gender of the borrower. We have age of the borrower. We know the reason for the loan. Was this a home loan? Was this a car loan? Was this some other type of loan? We understand the home status. So this is, does the borrower own their own home? Are they having a mortgage on their home? Are they a renter? What is their housing status? We have a credit score, of course. We know the annual income of the borrower, and we know what the loan amount is for the borrower. So this is the data that we have on current loans that have been issued from this financial institution. Now, there are a lot of things that aren't in here, right? Like, there's no debt to income ratio. There are other factors that might go into this decision that we just don't have access to right now. So the question right here is, are you comfortable making decisions with the data here? Would you want to get additional data, like what zip code they live in? What other kinds of things are out there that you might want to use to inform the decision? Are there any fiduciary requirements, like certain data you're not allowed to capture for legal or ethical reasons, or other data is required to be on hand to be able to make financial decisions? If you don't have the data, you need to make a decision of, can you find it somewhere else? Or are you going to have to go and pay to acquire new data? So as I was saying, there are a lot of other potential data that you may want to get, and you may not have access to it. So even if you were able to go and get new data, it's not necessarily the population that you have at the financial institution you're looking at, and it may not be as good. So you're going to have to make some trade-offs on the data, and it's not just a matter of, is the data right or wrong? It's what is your preference, what is your choice? You may want to be clear about this up front before you invest in an analytic effort, because as you're going to see throughout this lecture, there's a lot that goes into an analytic effort, and you might want to be in agreement that you're actually pursuing that investment using a data set that everybody agrees is the best that you have, or the ideal one for this use case. The next step in operationalizing data is becoming one with the data, right? And you really need to just spend some time understanding it, getting intuition in it, and these sorts of things. And so I'm showing you some simple, Python code here of things you can do. If you import a data file, you can look at, well, what are the data headers? I told you what the fields were, but you want to make sure, can you see what they are? Do you know where they're located? Is this structured where the data fields are in columns and the individual data points are in rows, or is it the opposite? How is that structured? What's the shape of the data? How many rows do you have? Do you have a column for every data field in your schema? What is the type of data? Are they integers, floats? Are they in some other kind of format? Are they strings? Because if you think you need numbers and you have the data comes to you all as strings, you may need to convert that, right? So you need to understand what kind of the data types it is. You may want to understand, are there duplicates? Is the same person represented multiple times? In which case that wouldn't be an issue. Or is there conflicting data, right? If the person's in there a couple times, does the data even match? Are there missing values, right? So for certain IDs, for certain customers, do they have missing fields, or is all the data there? And what kind of patterns exist in the data, right? You might want to do exploratory data analysis to visualize that. And I like to make the point here that exploratory data analysis, although it is quantitative, it is still very much a qualitative exercise. You're not wanting to make decisions based on observing random patterns in the data, because we usually set our error rate around 5% in a lot of just standard social science type applications. Well, that means that 1 in 20 times you're going to accidentally be wrong, right? You're going to conclude that something's wrong when it's right? You're going to make a mistake. And so the more you look at just random patterns without a driving hypothesis or without a driving theory behind it, the more you're likely to fall upon spurious conclusions. So what you're doing with exploratory data is you're just trying to understand the data, understand the relationships between them, and then you're going to want to kind of bounce those ideas that you come up with off of one of the domain experts that probably has a lot more industry experience using the data, and they'll be able to tell you whether they think it's spurious or whether there's basis for that. And this is really just so that you can get comfortable in understanding the data and what it's about. It's helping you get in touch with the domain and the requirements that you're trying to serve. So here's some observations. In the particular data set that I'm using here in this example, we can look that about 2/3 of the loans are good. So the term of the loan is interesting. Most of the loans are 3-year loans. Most of the borrowers are male. We can see that the home status, most of the borrowers have their home mortgaged. The next biggest group is renters, and the people that own their home are much less likely to get one of these types of loan statuses. So these are just some observations that we're doing as we're exploring the data, right? We're doing exploratory data analysis and just trying to understand what some of the differences are in the data. We can also look at the age groups, right? We're seeing that about half the loans are going to people in their early 20s. The other half is people over 25. We can also look that a lot of the loans are going to people with relatively low credit scores between 300 to 500. Less are going to people with credit scores over 500. And so when we're doing this type of exploratory data analysis, I'm just going to provide this list of 9 things or 9 reasons why you're doing this kind of exploration and you're just trying to become one with the data. You want to understand the data structure and content, what's there, what's not there. You want to get some idea of data quality, right? Is there missing data? Is there inconsistent data? Are the data schemas listed kind of slightly differently? You want to get some summary statistics like we've just been looking at. Are there any relationships between the variables? do you see any patterns in the data, right? Do you see any shapes, right? Is this linear relationships? Is it absolutely, nonlinear relationships like curved patterns? You want to try and get an idea for what are potential features you want to use in a machine learning algorithm, or what is a target variable that you want to predict or understand about? What would be a good proxy variable for some of the objectives you're looking to understand in your requirement? Are there any anomalies in the data? Anomalies might provide unusual leverage if you have an undersampled class, and you might want to remove those, or you might want to be aware that there's potential issues or leverage or bias in your findings if the data has some weird anomalies that aren't like the rest of them. Is there any kind of context you can develop from the conversations that this exploration will enable you to have with the domain experts that you might maybe weren't able to have initially? Our next step in operationalizing data is data cleaning. Now, we do data cleaning after you've done some exploratory data analysis and you've kind of become one with the data. You'll be able to identify some of the issues. And so we do this to identify and correct any of the errors, any inconsistencies, inaccuracies in the data. So this is making sure that the data is correct. We're not saying, is it the best to model our solution with, or anything like that. We're not talking about necessarily even integrating the data. We're trying to say, can we identify problems in the data and get it fixed so that it's ready for modeling? And this is something that the data engineer will do. And there are certain clear checks and tests that you can do to kind of identify potential issues. So, our example would be, let's look at the loan purpose, right? That was one of the schemas. So I can look and say, well, what are the unique purposes of the loans in this data set? And so what we see house, car, personal, other, wedding, medical. Oh, and there's another other. Well, I might make the conclusion that other with a capital O and other with a lower O, case O, are really the same thing. It's this miscellaneous category. I may want to then go and check that with the domain expert to make sure that I'm not missing something. But then when I've noticed that these are two of the same things, I can consider that an error in that the purpose was entered with a capital O or a lowercase o. And there's certain things where certain techniques where people might just move everything to lowercase, which would automatically resolve that. There's other little tricks that people do to try and catch problems like this. What we're going to do here is just, in this case, I'm going to give you a single line of code, and we're going to replace lowercase other with capital other. It'll be consistent with the other capitalization in the data set. And so this is how we're going to clean the data and get it corrected. And you can do this with all 10 of your data fields that you were looking at to make sure there's no issues. And there's a lot that goes into data cleaning. It's limited really only by your own creativity or experience. As you run across mistakes or problems, you'll think to check that in advance next time. Now, there is one thing that I would like to point out with data cleaning. All of these tests, right? All of these steps require time, and time requires labor cost, and so they can be expensive. So it is generally not recommended to go in there and say, just clean the data, or to say, find out if there's any issues in the data, right? Like, these are not very good. What I would require as a project manager or as a team lead is I would ask the data engineer to provide me with their testing plan. And a testing plan is, hey, maybe you've done the initial exploratory data analysis and you have looked at the number of fields and some of the relationships in the fields and some of this stuff initially to get a general initial feeling. But now I want to know, what are you going to go and test? And who is doing it? If it's a junior data engineer or junior analyst, great, but you need to give that person guidance. You don't just tell them to go and clean the data or go and fix the code. You want to make sure that they have a plan, there's a checklist, and that they've actually accomplished all the items on the checklist. This prevents rework. It also creates a learning log, so to speak. So if you're doing this on one step in the project, for one task, and you're doing this in a larger project, well, let's say a month into it, you find that, oh, you're in the middle of the analysis and you found that there was an issue you didn't correct in data cleaning. Well, that gets noted, and now we're going to go and add it to the checklist for data cleaning so that the next time we actually catch it. Or if we see that there's a whole bunch of things that are never an issue, well, then maybe we're going to remove those so they're not wasting time and money testing something that's never an issue. But you need to have a plan. You need to have clear guidance to the junior engineers that are on the project with what they're doing. And you want to have that be a continually improving process, right? So this all goes into the data cleaning. We're going to look at bivariate relationships. So these are understanding how data might have patterns together, right? So this is showing you delinquency or non-delinquency between male and female. And so we're just trying to look and see, hey, are there any dependencies in there, right? Is one gender more or less likely to default on a loan? We don't really see any patterns in this data right here. And just because you do see a difference, it could easily be confounded with something else, right? Like what if male borrowers, not to be stereotypical, but what if male borrowers happen to be more likely to be buying automobiles and female borrowers are more likely borrowing for a wedding? And so is it the loan purpose or the gender that's the issue? Well, you can't tell because they're telling you the same things. So these are some of the things we're trying to look at and get an initial intuition into the problem area. So once we have operationalized our data, we've got it ready for analysis, we're going to go into the analytics step. And this is where we're going to develop mathematical models that are going to analyze the data, analyze the patterns in the data to help us make predictions or decisions. And this is really the core of how we derive analytic insights, and they enable intelligent automation as well. So this becomes the next step. If you're receiving the data and the requirements, and you don't feel that the requirement has been defined very well, or you don't have a clear understanding of the data, you may need to have a few more iterations before you can really proceed into this analytic step. So what are some of the analytic decisions you're going to make? Well, the first thing we're going to do is, if we're doing machine learning and AI, we're probably going to randomly split the data. Training data, test data, maybe validation data, right? So we're going to, or are you going to do some sort of stratification? Right? Is there some reason why you are going to segment this data differently than random? What type of error are you going to try and minimize? Right? So are you going to try and minimize error like from a precision perspective so that when you say it's the object, it's the object? Or are you trying to minimize recall? Do you find all of the objects? Right? So if for example, I'm wanting to make sure that I do not give bad loans to people, right, then I probably want to be focused on recall because I want to minimize that higher cost of mistake. But if I am doing fraud detection and I'm going to make a decision to hold up somebody's credit card transaction because I think it's fraudulent, I may want to be precise so that I'm not inconveniencing the customer, right? So what type of error do you want to minimize? When we talk about errors, we can talk about false positives. And so in the loan example, this is where you're awarding a delinquent loan. So you're predicting that this is a good loan to give, but in reality it was bad. We also have false negative. So this is where we are going to be failing to award a good loan. So we predict that this is a bad bet, but it really was a good person to loan money to. In the loan application sense, it's worse to award a delinquent loan than it is to not award a good loan, right? So the delinquency costs more than the money you'll make from a good loan. So if we're going to be biased, we probably want to be a little bit more biased towards recall. We want to prioritize recall over precision in this example. And I use this because as you look at the other lectures that I'm going to talk about, I spent a lot of time talking about why precision is important. And I just want to make a point here that precision, when you hear me harping on about that, it's about making sure that the data is labeled consistently. So what I would always do is look at training data and ask domain experts to have multiple domain experts look at training data independently, make a decision on the label, and see how consistent they are. And if they are inconsistent, your precision is going to be degraded. And that can be improved simply by asking them to improve the standards and the rules, or understand why they're labeling things differently, so that you can get a better standard going, so that as you acquire new data, you're getting that greater consistency to boost precision from that perspective. What you're doing in the analytic modeling, however, right, is a different question. The analytic modeling is now, is the end result in this, like, we have the data we have. We're not going and getting different data or throwing data away or getting more data. That was all done in the operationalized data phase. In the analytics phase, we're making a decision about what is a bigger impact on our objective. And based on that, do we want to tune our models to prioritize recall or precision? So same metrics, right? But it's a different place that we are looking at what we're doing with that. So we're now going to train our decision tree algorithm on our data set. So we have training data, and what we do is we train the parameters for the decision tree on the training data, and then we apply it to the test data to see how well we did. And so what we're going to look at is something called the confusion matrix. And so what the confusion matrix does is on the y-axis there, it's saying what is the true label, right? A 0 is a bad loan, a 1 is a good loan. And what does our decision tree predict? 0 is again a bad loan, 1 is a good loan. And so what you see here is the red square in this case, right, is showing that, hey, this is a bad loan, and we predicted accurately that it's a bad loan, right? That makes up for almost 33% of the loans in our data set. And about 63% of the loans are, hey, we said it's a good loan, and it indeed was a good loan, right? So that was kind of matches what our exploratory data analysis told us before, right? About 2/3 are good and 1/3 is not so good, right? And then the black squares and the off diagonals are mistakes. So the upper right one is saying that it was a bad loan, but our decision tree thought it was good. And the lower left is saying that, hey, this was a good loan, but we denied them. And so we can call these things the false positive or the false negative, right? And this helps us understand how well this worked on the training data. We can look at the performance of the training data, and you see that we have pretty good accuracy. We have almost 96% accuracy. We have 94% recall. So when we say it's a good loan, it's a good loan. We have 99% precision. So we've pretty much found all the good loans. Our F1 score, very similar to accuracy there. But when we apply this model now to the training data, or to the test data, we have a different confusion matrix, which doesn't quite look as good, right? So you see that there's a lot more in that false positive, false negative squares, right? That's actually 45% of the data. So when we look at the performance, you'll see that on the test data, our accuracy was actually about 55%, recall 64%, precision 67%, F1 score 65%. So it's a lot worse. And so what we're going to go through now is what are some of the things we can do to now improve this decision tree so that it does a better job on this loan problem. Well, the first thing we can do is we can visualize the decision tree. And there's many different ways people look at to do that. Now, the decision tree is going through a bunch of different decisions through those 10 fields, and it's saying, hey, if it's this, if it's this, if it's this threshold, do I look at splitting this into 3 or 4 or 5 different value sets, or how am I navigating through all these different combinations, right? And so you can see that tree is pretty large over there on the left. You can also look at it as hierarchical, there, like, hey, is the purpose of the loan a wedding? Is it personal? Is it, right? Like, there's a whole bunch of different hierarchical questions or decisions, slightly different way of looking at that. Or you can just look and see what features seem to be the most important in making decisions, which bubble up to the top, right? And these are all things that are done in the decision tree algorithm. And we just talked very briefly about that in lecture. But, these are helping you get some intuition at what's driving the decision, and it's helping you get some intuition on what you can change. what this does is it helps us go into the area of hyperparameter tuning. So a parameter is a value that you're going to like maybe set a different threshold, or you're going to set a different value for. But the hyperparameter are, what are some of the levers that you can pull on in a decision tree to make it do better, regardless of what the actual values of each of those parameters are. And so the first one that I want to talk about is the maximum depth. So the maximum depth of the decision tree is the number of levels from the root to the deepest leaf. And what you're doing is you're adjusting for over or underfitting. If the depth is too shallow, right, then you're going to underfit the data. You have too simple a model, and it's not going to be that accurate. But if you have too deep of a leaf, you're really maybe just learning patterns in the training data, and it's not really going to generalize well to other data, which is our situation right now, right? Keep in mind, we had great performance on our training data, horrible performance on our test data, which tells us that we are probably overfitting the model, and we need to shallow up the depth a little bit to get better performance. Criterion. This is the function used to measure the quality of a split. So now, when you're building a decision tree, what's the threshold of going left or right on the tree or on the branch, right? You have a function that is telling you which way to go. And so, the two most common are Gini and entropy, and we're not going to go into depth on those, but the Gini is faster, and entropy is going to be providing better understanding of splits. So typically they're about the same, and so we might go with the Gini as a faster method. But if we don't like our performance, we might try entropy, but it's going to take a little longer to train, depends on how big our data set is. Splitter is the strategy used to split at each node. Are you going to do the best split, or are you going to do maybe a certain random parameter in there to make it a little bit random? And what that does is it kind of mixes it up and prevents it from just learning the patterns of the data, so it reduces overfitting in noisy data. It's kind of like another way of reducing overfitting, similar to like shallowing up the depth, but it's just a different way of doing that. And which one is better? I don't know. You have to try them both. And then minimum impurity decrease is required for a split to be performed. So this is basically talking about pruning certain branches. So we're saying that certain branches, they might improve the accuracy, but are they really worth the extra complexity, which might lead to overfitting? And so there is a cool little equation in the decision tree that allows you to kind of evaluate that. And so you can explore different parameters for what's the criteria for pruning certain branches off of the tree to try and simplify the model, reduce overfitting, and make it a little more explainable. So with all of those things, you're going to run a function in the code, and that's too detailed for what we're doing here, but you're going to try and optimize these hyperparameters. Now you can see that there's several to play with, and so some people, if the data is small enough, if the problem is small enough, they're just going to try everything, and they're going to let the package make the do the best optimization, and they typically do that with some type of what we would call gradient ascent, where they're changing a bunch of these different parameters and seeing if it's getting better, and it's a lot of trial and error until it kind of gets to the top. But if your data is very large, if the cost of training your model is very high, then you may want to look at statistically designed experiments or response surface optimization, which is a much more complex application of statistics to be more prudent about what parameter choices you're attempting to do in that optimization. But for our purposes, we're just going to let the package run. And what we see is we get a new confusion matrix. And so in the new confusion matrix, right, our initial performance, test performance, I'm only going to be looking at the test performance for the rest of these, but it's the similar. We train and then we test. The training is usually better than the test. So the initial performance that we got, you saw that the accuracy there was 55, recall 64, precision 67. Well, with our tuned test performance, this is after we've optimized the hyperparameters, and you can see that we're able to get a huge boost in recall for a very equivalent precision. So the precision is about the same on either one, and keep in mind I'm optimizing this for recall, so I'm able to get an almost 30% boost in my recall by doing the hyperparameter tuning on this model. So we're not done yet. So we've now kind of done this hyperparameter tuning, and the next thing we want to do is complexity reduction. And so we do complexity reduction again, to evaluate whether, at this point in a decision tree, we want to evaluate whether a tree branch is more expensive than its benefit, right, in accuracy. And what do I mean by cost? Well, is it allowing us to get the best recall at the end of the day, or is it still trying to learn patterns in the training data and kind of learn the test, not necessarily be able to generalize to new information? And so this pruning, again, is another way of controlling for overfitting and making sure that this generalizes better to new data. We can always tell that there's an issue with overfitting if our test data if our training data is way better than our test data. And so what we're doing is we're making these paths of cost complexity pruning, or CCP, that is a sequence of possible pruning options. Do we do this tree branch or this one? Or do we do this one first and then a couple more before we get back to the other one, right? What is the path of pruning that is going to improve our outputs? And we're going to calculate this alpha value that represents the penalty for tree complexity. So when alpha is low, we have high complexity, we're not pruning that much. When alpha is high, we're much more likely, because there's much greater penalty for having a branch, and so we're gonna trim more. And this word impurity in a decision tree is just another word for error, right? So this is what we're going to do. And what it ends up doing is it creates a graph something like this, where as I look at the alpha rates, and so what I'm doing is each of these dots represents a model that I've kind of run, and so I look at changing the alpha parameter on my decision tree, and then looking at the error rates that I have, or the impurity that I have on the left. So as you see that as that alpha gets higher and higher, the error gets higher and higher as well. And so it kind of makes this, you can see that this is like a distribution of where is the ideal alpha to be drawn, so to speak. Now, we're trying to optimize for recall. So what we want to do here is we may want to then look at plotting our recall in our test data and our recall in our training data as a function of alpha. So what you can see is that when alpha is very low, we have this situation of overfitting, where the training data has much better recall than the test data. But as we move alpha higher and higher and higher, we're getting those closer and closer together until you get to the point where all of a sudden they are the same. And so it's the point where they're the same that we would say, hey, we're not overfitting or underfitting, and that might be the optimal value for alpha in our complexity reduction. And so the initial test performance here again was 55% accuracy, 64% recall, 67% precision. And now when we had our tuned test performance, we got better. And now our post-pruning test performance, you'll see that we actually have a little bit better accuracy. Our recall is 1.0, perfect recall, and we have just a slight degradation, but it's about the same precision, and we have better F1 score. So the key factors in this process are still the credit score, duration of the loan, gender, and the purpose of the loan. But this is now helping us identify what the key factors are in a loan decision, and now we have a model that is a much better performing model for making decisions about loan approval. Now, the last step, of course, is how are we going to deploy this, and how is this going to actually inform decisions? Do we want the model being presented to loan officers to help them in making their decisions? Are we concerned that there might be gender bias or some other bias that we haven't identified in the model? Do we want to have it as just an audit tool to kind of check to see, hey, are certain loan officers making better or worse decisions, and using it as an opportunity for retraining, right? There are a lot of things that you can do with the outputs of these models aside from just using AI to make a decision on the loan. Perhaps you even want to get the clear yeses out of the system and get them loan approvals instantly and take a little bit more time to look at other factors with people that might be questionable. So the way that we actually deploy the solution is actually oftentimes the more interesting piece of at-scale AI deployment. But what we've just shown you is in a case study of loan approval, we've walked through the ROAD, R-O-A-D process of how you would actually identify requirements, how you would operationalize the data in this particular situation and what that looks like. What are some of the steps in the analytic process using a decision tree, and then how you would actually deploy that in a real situation. I'm Dr. Ian McCullough from Johns Hopkins University. Thank you for listening.